In a brief practical note, there are no alarms planned this morning, so if one does sound, then it is for real, and so please exit the building. This room, the two doors at the back, the one at the front to your left, and we need to gather at the assembly point outside the Sir Alexander Fleming building on Imperial College Road. Now, this year's Athena Lecture forms part of Women at Imperial Week, which has once again been a highlight in the university calendar. The week brings colleagues and students together to recognise and celebrate the achievements and contributions of women across our community. We've already had many excellent events this week, lectures given by Professor Camille Kandiko-Hausen, Professor Ophira Ginsberg, who's one of our Provost's visiting professors, and of course, now today, we have the Athena Lecture. I hope you've enjoyed the events that you've participated in and that have been held across all of our campuses, not just here out South Kensington. And the week's not over, so I would encourage you as well to explore the Women at Imperial Hub, which features stories and profiles from across the university. So my thanks to everyone who's contributed to making this year's programme such a success. While this week provides an important moment for reflection and celebration, our commitment to gender equality is ongoing. As a founder member of the Athena Swan Charter in 2005, Imperial has long recognised the importance of building an inclusive academic environment in which all colleagues and students can thrive. And that commitment continues to shape many of our initiatives today. These include programmes such as the Provost Visiting Professors Scheme, which brings distinguished scholars from underrepresented backgrounds to Imperial, as well as our ongoing support for early career researchers and the development of women's academic careers. It's therefore particularly fitting that today's lecture is delivered by someone who's not only made exceptional contributions to science, but who has also been a visible and influential leader within Imperial and the global scientific community. Professor Michele Dougherty is our Professor of Space Physics and former head of the Department of Physics here at Imperial. She is also the Astronomer Royal, becoming the first woman to hold this prestigious position and the first academic from Imperial. Michele follows the likes of people like John Flamsteed, who was the first Astronomer Royal. He founded the Royal Greenwich Observatory and catalogued thousands of stars. Edmund Halley predicted the return of the comet, now named after him. Sir George Airy established the Greenwich Meridian as the international reference. Following in the footsteps of these historical scientific figures, Michele's work has been central to some of the most ambitious space missions of recent decades. She led the magnetometer investigation on NASA's Cassini mission to Saturn, and she's currently the principal investigator for the magnetometer instrument on the European Space Agency's Jupiter Icy Moons Explorer mission, which launched in 2023. Michele is a Fellow of the Royal Society, and she's received numerous honours, including the Royal Astronomical Society's Geophysics Gold Medal, the Institute of Physics Richard Glazebrook Gold Medal and Prize, and a CBE in the 2018 New Year's Honours. We're therefore extremely fortunate to have her as a member of our community, but also as our speaker today. So please join me in welcoming Professor Michele Dougherty.
Hello, everyone. Really nice to see you. It's always good to come back to Imperial. I spend at least a day a week here, so this week I'm spending 2 days. And what I wanted to talk to you about today are discoveries that have been made at the icy moons of Jupiter and Saturn. And I'm going to start off by talking about what we were able to do with the Cassini spacecraft and the magnetometer instrument on board Cassini when we were orbiting around Saturn, then talk about the mission that's going to Jupiter, and then I will go back to Saturn because I wanted to show you the end of mission for the Cassini spacecraft. So before we start looking in detail at some of the discoveries, one of the things I wanted to point out to you here is if you look on the image of Saturn on the right-hand side, sorry, I didn't mean to press anything. Can we go back one, please? There we go. If we have a look here, this is a view of Saturn from the Cassini camera on board, taken over a very long period of time. So lots of different images all put together so that we could see Saturn's system in its entirety. You'll see the visible rings of Saturn. You'll see sunlight peeping from behind Saturn. You'll also see another ring, which is called the E-ring, and that's something I'm going to talk to you about quite a bit today. And in the E-ring, you can see what looked like plumes emanating from the E-ring. And that was one of the discoveries that we made. One of the moons has got water vapor outgassing from its south pole. But the final thing I wanted to point out here is if you squint and look really carefully where my little green light is, you can see a blue dot, and that's the Earth. And every time I look at that picture, the hair on my arm stands up on end, because there was the spacecraft orbiting around Saturn, and while it was doing so, it was able to capture the Earth as well. And so that gives you an understanding about how good the instrumentation was on the spacecraft to allow us to be able to take those kind of images. So let's talk a little bit about the Cassini mission. So this gives you a view of the Cassini spacecraft itself. You can see it's covered with what looks like a gold covering, and that's a thermal blanket. That allows the instruments in the spacecraft to operate at a temperature where they can operate. So out in space, out at the orbit of Saturn, the temperature goes down to about minus 170 degrees Celsius. So we need to be able to have not only heaters on the instruments in the spacecraft, but this thermal blanket that try and keep the spacecraft and the instruments at a reasonable temperature. That big white umbrella-shaped object, that's known as the high-gain antenna. And once a day, what would happen is the spacecraft would turn back to the Earth, and it would send all the data down that it had collected the previous day. This object here was the Huygens probe. That was built by the European Space Agency, and that was released when we got to Saturn and actually traveled down through the atmosphere of Titan. And I'm going to talk a little bit to you about Titan in today's talk as well. And then last but not least, you can see this very long boom sticking off from the side of the spacecraft. That is where we put the magnetometer instruments that we build at Imperial College. So I'm going to talk to you a little bit about magnetometers and what they do. But what we do is we try and get them as far away from the spacecraft as we can, so the magnetic field we measure is due to the space environment and not due to the spacecraft. So we actually had one instrument which we built at Imperial halfway down the boom, and we had another one which was built at the Jet Propulsion Lab in California right at the end of the boom. And before I move on, you can see all the different flags of all the different countries that were involved. When you're involved in a planetary mission like this, having international collaboration is critical to be able to get the best out of the mission and the science results. No, there we go. Okay. So this shows you a view of the Cassini spacecraft in the test chamber before launch. And one of the reasons I like to show it, it gives you an idea about how big the spacecraft is. So you can see people standing at the bottom of the spacecraft. So it gives you an idea about how large the spacecraft is. What we do is we put spacecraft into test chambers like this to make sure that the instruments in the spacecraft can operate in the kind of conditions that we're going to see out in space. So at the very low temperatures, but also in the vacuum of space. So this was really one of the last tests that's done on the spacecraft and the instruments. Another thing you might notice is the magnetometer boom cannot be seen. And that's because you can't launch a spacecraft with a large 11-meter boom sticking off from the side of the spacecraft. So it was folded away in this canister that you can see here. And after launch, it was deployed on our way to the Saturn system. Okay, so I want to talk to you a little bit today about what the instruments that we build at Imperial College measure. So they measure the magnetic field. Now, this shows you a picture of the Earth. We all know that the Earth has a magnetic field generated in the deep interior. The reason we know that, lots of reasons we know that, but if you stand with a compass needle on the surface of the Earth, the compass needle is going to point to the north pole of the magnetic field. But in addition, those magnetic field lines, which you can't see, but if you could see them, that's what they would look like. They protect us from energetic particles in the magnetic field coming from the sun. So they essentially act as a barrier. One of the other things that I want you to keep in mind as we go through the talk is that as a planet like the Earth or Saturn rotates on its axis, so for the Earth it's once every 24 hours, for Saturn it's once every 10 hours, those red lines, those magnetic field lines are going to rotate at the same rate. And so if you're a moon sitting close to a planet, as the planet rotates, those magnetic field lines are going to impinge on the moon. And how they interact gives you an understanding about properties of the moon. And so that's one of the things that we were thinking about when we made when we took the data that we did from this moon called Enceladus. So, just to set the scene, this is the Saturn system. You can see, as I pointed out in that very first image, you can see the visible rings here. You can also see a number of the moons. So we've got Mimas, we have Enceladus, we have Tethys. Lots of moons all in orbit around Saturn. And you can also faintly see this E-ring that I pointed out to you. It's a large diffuse ring which extends out into space. You can't see it with the naked eye, but you can see it if you have instruments which are orbiting around Saturn. Now, two of the things that we knew before we had these flybys by the Cassini spacecraft of Enceladus, one of them was that the particles in not only the E-ring, but all of the other rings around Saturn seem to be made up mainly of water ice. And we long wondered whether Enceladus was somehow the source of this E-ring. It's sitting right here. And we knew from previous observations that the surface of Enceladus was made up mainly of water ice. So was Enceladus somehow feeding this E-ring? That was not what we were not sure about. Just keep in mind that Tethys and Mimas are two moons orbiting around Saturn quite close to Enceladus, because I'm going to refer to that in the next slide. So this shows you a view of the surface of Enceladus. It was taken by the imaging camera on board Cassini. One of the things that you will notice is there aren't many craters on the surface. There are only a few craters. And that was a real surprise, because Mimas and Tethys, the moons that are orbiting close by, their surfaces are covered in lots and lots of craters. And so the implication was that something was going on at Enceladus that was making the surface younger than the moons close by. We didn't know what that was, but it was very clear that there was some kind of resurfacing that was taking place. But the thing that will also catch your eye on these two images is these very deep cracks on the surface. So we arrived at Saturn in July 2004. It took us 7.5 years to get there. It's one of the things about planetary missions. You need a lot of patience. I'm not renowned for my patience, but somehow I keep on doing this. So we had 3 flybys planned in 2005. The first flyby was quite a distant flyby. You can see the altitude of the flybys below here. First one was just under 1,300 kilometers above the surface. A month later, there was a second flyby planned, which was 500 kilometers above the surface. And then 3 months after that, we planned to fly past Enceladus again. And originally, we were going to be 1,000 kilometers above the surface. But based on observations that we made on these first 2 flybys, we were able to persuade the Cassini project to take us much closer on the third flyby. And I'll actually talk you through that so you can see how we came to the realization that we thought something really interesting was happening at Enceladus. So this is a snapshot. We would get the data down every 24 hours, as I mentioned to you. And this is a snapshot of our first view of what the data looked like. And this shows you the software that we were running. It was essentially a screenshot of the computer screen showing us the data. Now, the way the magnetic field works, and that's what I should have said, sorry, when I was talking about the magnetic field. If you think back to that view of the Earth and the field lines, one way to think about a magnetic field is if you've got a piece of paper, you've got a bar magnet underneath that piece of paper, and you put iron filings on top of the paper, those iron filings are going to lie along the lines of force of the magnet. And so that's essentially those magnetic field lines that we could see. So magnetic field has a strength and it's got a direction. So what you do is you measure the three components of the magnetic field that you can see there, those top three panels, and you then use that to work out what the strength of the magnetic field is, which is that bottom panel. So this shows you 24 hours of data. You've got to be a magnetometer person to be excited by this, but give me time. Let me just try and excite you as well. So what I'd like to point out is if you have a look at this particular component, it seems to be smoothly changing over time, but then something very different happens for a short period of time. You look at this larger component down here, and if you look really closely, there's a little pimple on the data. Third component is behaving like this, and then something very weird happens. And in addition to that, the data seem to get pretty noisy on either side. That was as we were flying close to Enceladus. So that was telling us that something was happening. We didn't quite know what it was. So what we needed to do was look much more closely at the data. So what we did, first thing we did is we subtracted the magnetic field of Saturn away from the data so that we were left with something that looks like this. So now what you're doing is you're looking down on the north pole of Enceladus. Saturn is off here somewhere, and the magnetic field lines and the plasma from Saturn are coming from the left. Sorry, Saturn is up here. The plasma is coming from here. And this shows you the trajectory of the spacecraft. And overlain on top of it are these little vectors. And that is what is left in the magnetic field once you've subtracted the Saturn field away. And what it seems to be saying, if you look at it, is that something is stopping the magnetic field from actually penetrating down onto the surface. It's almost as if Enceladus is a much larger obstacle than it looks. Something is holding the magnetic field away from the surface of Enceladus. But not only that, all of that noise that you saw in the data, you can analyze that noise and you can work out what is making that noise happen, and it was a large increase in water group ions. So we had what looked like a really strange signal. We had an increase in water group ions, and we thought maybe Enceladus is actually generating those water group ions. But one of the problems was that I was a little concerned that we hadn't had time to calibrate our data properly. One of the things you do if you fly past a moon is you want the camera to keep the moon in view all the time. So you're moving very quickly, and it takes a few days to get the proper trajectory data back from the spacecraft. They need to give you the best data they can. We were looking at the first version of that. So we didn't say anything to the Cassini project. We then had the second flyby, which seemed to show something very similar. And the fact that those two flybys were 2 months apart and we saw the same signature seemed to us to be saying that something really interesting was happening. So what we did is we put together this little schematic to try and describe what we thought we were seeing. So there are two different views you're going to look at. For the first view, your eye is up here, looking down on the north pole of Saturn. So here's the north pole of Saturn. The gold rings are the visible rings. The blue lines are the magnetic field lines that are rotating at the same rate that Saturn does, and the little orange ball is Enceladus. If Enceladus was a dead body, those blue lines wouldn't see it at all. They'd move straight through it. But what we seem to be seeing, and now your view is, you're looking sideways on Enceladus, and what we seem to be seeing is here's Enceladus, here are the magnetic field lines of Saturn, and something was stopping the magnetic field lines from penetrating down onto the surface. One way that you can do that is the following. If you've got an atmosphere. Oh, I think the room's decided we're getting really hot and it's spewing out cold air. That's not me, I promise. So, if you've got an atmosphere, just like we have on the Earth, the upper regions of the atmosphere become ionized, and that stops the magnetic field lines of the solar wind penetrating down onto the surface of the Earth. So that's how we get protected. So what we did is we put this little schematic together, which showed that we thought Enceladus had this diffuse extended atmosphere, which was essentially acting in the same way as it does on the Earth. And this was an important enough result that we decided that we should try and persuade the Cassini project for the next flyby, 3 months later, to go really close. So I remember I flew out to the Jet Propulsion Lab to try and make the case. I was a little bit nervous because we had planned every second of the observations we were going to make at Saturn. All the instruments knew what they were going to do. And here I was coming in saying, oh, can we just change that, please? Can we use fuel, spacecraft fuel, to actually change what we were going to do? And the meeting we were going to have was at about 11 o'clock in the morning. I'd arrived the night before, jet lagged, didn't know what time of the day it was. So I decided to buy a coffee. And I was standing in line at the Starbucks just outside the Jet Propulsion Lab. And the man in the line in front of me turned around to me and said, Michele, what are you doing here? His name was Jerry Jones. He was responsible for the spacecraft. And I told him what it was I wanted to do, and he rubbed his hands together in glee and he said, oh, that's really cool. I've always wanted to go closer to a planetary body than anyone else. So I had one vote in my back pocket when I went into the meeting. It was a difficult meeting, though. We talked about it for a couple of hours, but there was enough consensus that everyone thought it was important enough that we went really close on the next flyby. And so that was the plan. 3 months later, we would fly really close to Enceladus, and fortuitously, and you'll see why I say that in a second, that close flyby took us below the south pole of Enceladus. So July started approaching, and for a couple of nights before the flyby, I must confess I didn't sleep very well, because if we hadn't seen anything, no one would ever have believed anything I said again. But this is what we saw. Instead of there being an atmosphere covering the entire surface, there was a plume of water vapor only coming from the South Pole. Because we were so close, all the other instruments took some great data as well. So let me talk you through that data. So this is 2 data sets. Top left, we have from the imaging camera, and you can see that at the South Pole, there were these cracks, or what the imaging team called tiger stripes at the South Pole. Bottom left, we have data from an instrument that was able to remotely sense the surface of whatever body it was looking at. What they thought they would see is that the hottest temperature would be at the equator, because that's where the solar radiation is strongest. And they did see it was hotter at the equator, but they also saw there was a hot spot right at the South Pole. Now, those of you who know what Kelvin is versus Celsius will see that we're not talking about hot here. We're talking about 85 degrees Kelvin. But out at Saturn, that is pretty hot. So we had a hot spot. We put those 2 data sets on top of each other, and the hottest region was lying right over one of the cracks, with the implication being that internal heat coming from the interior of Enceladus was leaking out through these cracks. So what we had, based on data from 3 different instruments, is we had water vapor emanating from these cracks at the South Pole, and we had internal heat leaking out as well. Now, one of the things, if you do outer planetary exploration, is one of the things that you keep in mind is, are the ingredients there for life to be able to form? And our understanding about how life forms on Earth is you need liquid water, which we seem to have at Enceladus, and it turns out we have. Gravity data now confirms there is a liquid water ocean at Enceladus, and it's under pressure leaking out as water vapor. You also need a heat source, but the third thing you need is organic material, and then you need those 3 ingredients to be stable enough over a long enough period of time that something will happen. And that's what we found. We found organic material in the plume. So this is data from an instrument called the eye-neutral mass spectrometer. And the way it worked is, as you fly through the plume, it takes the material into the instrument, and it's able to resolve what is in the plume. What they found was water vapor, which we knew from our data. They found methane, carbon dioxide and carbon monoxide, but they also found signals of both simple and complex organic material. So that meant we had the three ingredients that we think you need for life to potentially form. So following on from this, there was a real focus on Enceladus. We had, I think, another 30 flybys of Enceladus and the rest of the mission. And there's now a mission planned by the European Space Agency in the future to go into orbit around Enceladus. So this is one of the places in the solar system where life might be able to form. We talk a little bit about Titan. This is one of the other moons of Saturn. I mentioned right at the start there was a focus on Titan. The European Space Agency Huygens probe was going to travel down through the atmosphere. But in addition, the Cassini spacecraft, I think, flew past Titan about 120 times. One of the weird things about Titan is that you can't see down onto the surface. There's a hydrocarbon haze, almost like a fog, which doesn't allow you to see down onto the surface. And it was only once we got to Titan with some of the instrumentation that we had on Cassini that we were able to see through the surface. One of the reasons we were interested in Titan is it's got a very deep atmosphere, about 160 kilometers in height. And we, at the time, thought that its atmosphere was very similar to what the Earth's atmosphere was like when it first formed. So one of the reasons to go to Titan is to try and get an understanding about how Titan's atmosphere in its form now has evolved into the Earth's atmosphere. So that was the original focus of Titan. We think its chemistry is very similar to what our Earth's atmosphere was like. So the Huygens probe traveled down onto the surface of Titan, and as it was traveling down, it saw what would look like old lake beds where liquid had certainly moved on the surface in the past. But for the first 3 years that we were in orbit around Saturn, we couldn't see any liquid on the surface of Titan at all, until eventually there was this glint of sunlight off a lake right at the North Pole of Saturn. And we couldn't understand why we hadn't seen it before. And there was a lot of work done trying to understand that. Turns out the season was wrong. The first 3 years we were there was the dry season for Titan. There hadn't been any rain. And then suddenly we moved into the wet season and rain began to fall. Not liquid rain, not liquid water, but ethane and methane. So that's when we began to see liquid on the surface. This here shows you a view of Titan which was taken from the visual infrared mapping spectrometer. So it was taken at a wavelength which is not at visible wavelength, but at infrared wavelengths, which allowed you to see through the haze. And so this gives you our first view of what the surface of Titan looks like. Around the equator are these sand dunes. The brown regions is sand dunes essentially all the way around the equator. The pale blue regions are water ice. Just in here, you can see a rather strange shaped object. That is an ice volcano, and there were some really close-up images of that, and you can see how liquid had come from underneath the surface and had flowed onto the surface over time. And there was a large impact crater here as well. So that's why a spacecraft like Cassini is so important, because it allows so many instruments to fly on it that you can see things at wavelengths that you wouldn't ordinarily expect to make discoveries. And if we hadn't had this infrared instrument on board Cassini, we simply wouldn't have been able to know what the surface of Titan looked like. And then the last thing I wanted to say about Titan is this is based on gravity data from all of the flybys we had at Titan. Based on the gravity data, what we have worked out is that there is a global, in this blue region here, there is a global subsurface water ocean underneath the surface of Titan. So that means there are 2 moons at Saturn, which have got liquid water. Enceladus, we know, has also got organic material. The question about Titan, we need to look at more closely. But that means there are at least 2 moons in the Saturn system which might have the potential for the ingredients for life to be able to form. Sorry, I'm getting mixed up with the buttons. There we go. Okay, so let's move to Jupiter for a bit. There was a spacecraft called Galileo, which orbited around Jupiter in the late 1990s. And based on magnetic field observations of the moons and gravity data, this is what we think the internal structure of the 4 large moons of Jupiter looks like. So Io in the top left has got a deep core, doesn't have a liquid water ocean under the surface, but it's got sulfur volcanoes on the surface, and it's spewing out a lot of sulfur dioxide all the time. So it's a difficult place for spacecraft to survive. So the JUICE spacecraft I'm going to talk about is staying far away from Io because we want to focus on the other 3 moons. So the other 3 moons are Europa, Callisto, and Ganymede. And based on magnetic field observations, we are almost certain that those 3 moons have got liquid water under the surface. And you might be asking yourselves, how can a magnetometer instrument tell you if there's liquid water under the surface? Well, the way that it works is if you've got a conducting body, which is my hand, and you've got a magnetic field that is changing around that conducting body, that changing magnetic field induces electrical currents in the conducting body. Those electrical currents generate a magnetic field, which the instruments that we build at Imperial are able to measure. So that's how you can predict that there are these liquid water oceans. So, very busy slide, I will talk you through it. What we're looking at here is what I think is the most important realization that planetary scientists have come to in the last 3 to 4 decades. And that is that you don't have to be close to the sun for a planet or a moon to have liquid water. You can go quite far away from the sun. So let's have a look at this. What we're looking at here is that's our sun. These are other suns in the universe, but we've got our sun just there. And as we're moving away in distance from our sun, we've got all the planets in the solar system. Until about 40 years ago, we always assumed that you needed to be inside what is called the snow line. So that's where if you have liquid water on the surface, inside of that line, it's liquid, beyond that line, it's ice. So we had always focused our interest in finding liquid water on the planets inside of the snow line. But the Cassini and the Galileo observations have confirmed to us you can go beyond that snow line. You can, at Jupiter, potentially have deep habitats at 2 or 3 of the moons, and at Saturn, you can have these deep habitats at Enceladus and Titan. So that was a real focus, a real change of focus as far as planetary scientists were concerned. And in fact, we used this slide when we presented to the European Space Agency, trying to persuade them that we wanted to go back to Jupiter. And people have asked me before, why not go back to Saturn? Well, at that stage, Cassini was still orbiting around Saturn. There was a lot more we could learn. So that's why we thought going back to Jupiter would be the best next step to improve our understanding. This shows you a view of what the environment around Jupiter would look like if you could see it in the night sky. So I've told you you can't see the magnetic field lines with your naked eye, but you can measure what they look like. That's what they would look like. But the reason I want to show this to you, it shows you how big the Jupiter environment is. Compare it to the size of the full moon. You can see how vast an area of space it looks like. But it also reminds me that when I was a kid in South Africa, my first view of Jupiter and its moons was through a telescope that my dad built, never thinking I would end up doing what I'm doing today. So this is what the JUICE spacecraft looks like. I'll actually show you a picture of it just before launch. But a few things to point out. The main source of power for the JUICE spacecraft is via solar panels. There is fuel on board, but the way in which the instruments are going to be operated is by solar power. And you can see how large they are. I think it's about 76 square meters of solar panels. And once we're out at Jupiter, which is quite far away from the sun, they will produce about 80 watts of power, which will allow us to drive the instruments. The high-gain antenna that I pointed out to you on Cassini, we have a similar high-gain antenna on JUICE as well, where again, once a day, once we're at Jupiter, we'll turn and point to the Earth and actually stream the data down. And then the magnetometer boom, which we put our instrument on, is just below the spacecraft here. And again, we're on this boom so we can be as far away from the spacecraft as we can. This shows you some images in the lab, in the Huxley building, just across the way, showing you the instrument as we were building it, but also just to remind me to talk about how difficult it was to build, because this was going on during COVID lockdowns. And I never told Issa this until after the instrument had been delivered, but some of the early models that we built happened right at the start of lockdowns, and some of the engineers took some of the parts home to start putting them together. Never told Issa that until after they accepted the instrument, but we had 3 or 4 months where we were not allowed back in our labs, but slowly we were allowed back in the labs. And what you can see is the entire instrument on this bench here. So this instrument here is the fluxgate that we build at Imperial College. There is another one which our German colleagues in Braunschweig built, and there is a third instrument which is a scalar instrument. It only measures the magnitude of the field, and we need that when we're in orbit around Ganymede. So the instrument suite consists of 3 different instruments, all on this very long boom. This here is the electronics box, which sits on the main body of the spacecraft, and it's then connected by all of these cables to the instruments that are on the boom. You've got to be made of stern stuff to watch some of this. So we have to test that our instruments can survive the rigors of launch, for example. So this here is the vibration table. And you stand there and you watch the baby you've been building for the last 1.5 years be shaken at the vibration loads it's going to meet when it gets launched, hoping that one of the sides doesn't fall off, and it didn't. But you are a little bit nervous until you get through the test. And this one here is known as the shock test. There is a weight that's essentially dropped on the e-box to see if it survives. If it doesn't, you then have to start again. But there are all these different models that you build over a period of about 4 years until you get to the final model, which is the model that you will actually put onto the spacecraft. In addition to that, you build a flight spare model, which we now have in the lab just across the way. And what we do is we send commands to that flight spare instrument before we send them to the spacecraft, just to test them out. This shows you a view of the Antonov aircraft, which took the JUICE spacecraft over to French Guiana, where it was going to be launched. Preference is you get launched from as close to the equator as you can, because that's the way where the gravitational field is less, so you need less fuel if you're being launched from the equator. And you can see the nose of the aircraft opening up and the JUICE spacecraft being lifted out of it. This shows you the spacecraft in the launch chamber, just making sure that everything was ready before it was put on top of the spacecraft. Here you'll see the thermal blanket is black compared to gold like it was on Cassini. You will notice the solar panels on either side. Of course, they're folded away on either side of the spacecraft and get deployed after launch. And if you look really closely, you can see the magnetometer boom. There are 3 parts to the boom, and they, of course, were also folded away against the spacecraft so that we could launch them safely. Sorry, this little button has a mind of its own. There we go. Can't talk about a spacecraft unless you show a launch. These are 2 different images. Also, I will show you the launch itself. It'll be a bit noisy, so just prepare yourself. The spacecraft was due to launch on the 13th of April, 2023. And I remember we were all sitting in the mission control room watching the countdown. And about 10 minutes before launch, what happens is you send a balloon into the upper atmosphere, just above the launch site, just to make sure that everything is okay. And they sent this balloon up, and they found a lightning storm was taking place just above the launch site. And the launch window was a minute. And so we couldn't afford to take the chance of launching a 1.5 billion euro spacecraft into a lightning storm. So they scrubbed the launch for the day, and they brought us back the following day. And it was spectacular. Let me show you the launch. Prepare yourself, it's going to be a little bit noisy.
Vulcain. Allumage de EAP, décollage.
That particular video camera doesn't survive, but it does send the data back as it's going through the launch. So the launch was spectacular. The Arianespace, which is the launcher, got us to exactly where we needed to be. So we don't need to use any extra fuel to be able to get ourselves into the position to get out to Jupiter. We're en route. It'll take us another 5 years to get there, but we have enough fuel to be able to go really close to some of the moons. So what I want to talk about very briefly, before I go back to the Cassini end of mission, was just the main focus of the JUICE mission. We're going to be looking at 3 of the moons of Jupiter: Ganymede in the top right, Callisto in the middle, and Europa bottom right. Ganymede is the main focus. We're going to end the mission by going into orbit around Ganymede. And what we are going to do is the main focus is to get an understanding not only how deep the liquid water ocean is, but what its conductivity is, so its salt content, but also how deep the ice crust is above that ocean and whether it's a global ocean. Also, Ganymede's the only moon in the solar system that has its own internal planetary field, just like we have on the Earth. So that we want to try and get a better understanding of as well. Callisto, the moon in the middle, we think its internal structure is different to that of Ganymede, and we don't quite know why. But the other reason that Callisto is interesting, other than we think there is a liquid water ocean under the surface, a very thin one, is that its surface is very, very old. So it's going to allow us to understand the impactor history of the surface of Callisto. And then last but not least is Europa. We only have 2 flybys of Europa, partly because there's a very high radiation environment around Europa. But there's another mission called Europa Clipper, which NASA is sending to Europa. And so both of those spacecraft are going to be at the Saturn system, at Saturn. You see, I get confused, at the Jupiter system at the same time. Let me tell you what I lose sleep over. When I wake up at 2 o'clock in the morning, this is what I worry about. This is Ganymede. There are 3 different types of magnetic field that we want to measure at Ganymede. One of them is due to the liquid water ocean. So I said to you right at the start, we've got a conducting body, we've got a magnetic field from Jupiter that's changing. That magnetic field of Jupiter causes electrical currents to flow that change the magnetic field. So they will change the shape of the field because of this liquid water ocean, but the changes are really small. In addition to that, at Ganymede, we've got this internal planetary field, which doesn't change over time. That's one of the reasons why we think we can separate all these effects away. And then last but not least, we've got Ganymede embedded in the magnetic field of Jupiter. So there are 3 different magnetic fields we need to separate from each other. Fortunately, one of them doesn't change in time and 2 of them do. But the way I like to describe it is what you're trying to do is you're trying to find needles in a haystack, and those needles are changing shape and color all the time. So you need to be able to model them really well, and that's what the team is working on at the moment, putting models together so we can actually do this separation that we have promised ESA we're going to be able to do. Those red circle and ellipse, that shows you what the spacecraft is going to do, how it's going to orbit around Ganymede. One of the things I also wanted to mention is that by looking at Ganymede, which we think is a water world type body, by understanding a water world in orbit around Jupiter, it's going to allow us to understand a lot of the exoplanetary systems that we're beginning to discover. So it will allow us to get an understanding about a whole new class of body by going into orbit around Ganymede. So, just to put everything into context, let's have a look at the timeline of understanding some of the moons in the outer solar system. We started off in 1610 when Galileo first looked at Jupiter and saw the 4 large moons of Jupiter. We then had missions going to Mars which seemed to point to the fact that there had been liquid water on the surface of Mars. We had some experiments in the deep habitats on Earth, so in the deep oceans in the Earth, where the temperatures and the pressures you wouldn't think would allow life to form, but they found bacteria in those kinds of environments. We then had the exploration phase. We had Galileo at Jupiter, we had Cassini at Saturn, we had the first extrasolar water world discovery in 2012, and now we have what I call the characterization phase, which is the JUICE spacecraft and the Europa Clipper spacecraft focusing on some of the moons of Jupiter. Next steps would potentially be landing on one of these moons, and when we first proposed to ESA to fly JUICE, I was asked, why don't we just go and land? And the question is, which moon do you land on, and where on the surface do you land? Imagine how frustrating it would be if you landed on a moon and you found that you had 110 kilometers of ice shelf to get through before you could get underneath the surface. So this is part of the characterization phase, which is essential if we're going to go back and decide where we're going to land. So I'm now going back to Cassini, partly because it's a great way to end a talk, but I also wanted to just talk you through what we did at the end of the Cassini mission. I am keeping an eye on the time, so I won't be long. So the Cassini mission at Saturn was due to be 4 years in duration, but the instruments and the spacecraft were working so well they were extended, so the total mission was 17 years in duration. What we decided we would want to do at the end of the mission is we wanted to stay away from Enceladus. We didn't want to crash land a spacecraft on the surface of Enceladus, because if you find life at Enceladus in the future, there would always be the question mark is, did the spacecraft take some bacteria to Enceladus? You might want to ask me the question, why didn't we worry about that for Titan? So what we decided we would do is, for the last year of the mission, we would focus on Saturn. We'd focus on trying to understand what the deep internal structure looked like. We didn't understand the magnetic field measurements that we were making. So what we did is we put a two-phase process together. We used Titan to get us out of the equatorial plane. So we then moved ourselves into what we called the ring grazing orbits, where we flew just beyond the outer edge of the visible rings to get an understanding about this environment in particular. And then we used Titan again to change our trajectory, and we then had what were called the grand finale orbits, inside of the rings, just above the surface of the atmosphere. And let me show you some of what this implied. So this is what it would look like if we had been able to view the spacecraft going through this part of the environment. So the gray were the ring grazing orbits, and then the blue were the grand finale orbits. Other reason I like to show this is you can see the orbit through the rings, and that's because the rings aren't solid. They're made of countless individual particles, each in their own orbit around Saturn. But that shows you how close those orbits got to the top of the atmosphere. The orange orbit is the end of mission orbit. One of the reasons we wanted to do this is we wanted to try and understand where the magnetic field of Saturn comes from. We know it comes from the interior, but we wanted to understand the processes about how it looks different to the magnetic fields of Jupiter and the Earth. I don't have time to go into that in detail, but what we found at the end of mission, from the end of mission data, allowed us to better understand that, and we can always talk about that in the Q&A if you'd like to. This shows the view of the spacecraft going through this gap on the first close orbit that we did. And I remember I went to the Jet Propulsion Lab for it, and I bumped into the mission control manager, who looked really nervous. No spacecraft had ever done this before, and he was really concerned that we weren't going to survive it. But he did say to me, I'm not quite as nervous as I would be because all the spacecraft is protected by the high-gain antenna. So we went with the high-gain antenna pointing in the direction of travel. But he then pointed out to me that I should be really nervous because my instrument wasn't protected at all. It was on this long boom. So instead of being slightly nervous, I was then very nervous. But it was empty. There were no energetic particles there, and it was a safe environment to be in. So we actually did 22 of these, getting closer and closer all the time. So this shows you a view from the visual infrared mapping spectrometer, so a view of infrared view of what Saturn looks like, and that little ellipse is where the spacecraft entered the atmosphere of Saturn and began to burn up. Let me just put it into context for you. If you look at it, it was essentially just above the equator in the northern hemisphere. Sorry, I'm now getting confused between buttons. There we go. So this shows you a view in the mission control room right at the end of the mission. And it was really interesting. In the last 6 months of the mission, we had one of these close flybys to Saturn every 6.5 days. We were exhausted. And we were thinking, it will be a relief when the mission is over. And then it ended. And you suddenly finding yourself thinking, that's the last 25 years of my life. What am I going to do now? So that's where JUICE came from. But you've been working with international colleagues for the last 25 years, and then suddenly it ends. So it was a very difficult to process, actually. But for me, the most poignant part of it was this bit here. So this is the mission control room. These graphs that you can see here, as long as there is a spike on the graph, it tells you that the spacecraft is talking to the Earth. When that spike goes away, the spacecraft is no longer there. And we were watching that spike, and it disappeared, and then it came back again. And the reason it came back again is no one had told the spacecraft it was the end of mission. And the computer had been trained to keep its eye on the Earth. So it reoriented itself for as long as it could and continued to send data down. And then it couldn't do it anymore, and that spike disappeared, and that's when we knew it was the end of the mission. So I'm going to play you a video now, which essentially gives you an overview of the Cassini mission and also talks about the end of the mission as well.
A lone explorer on a mission to reveal the grandeur of Saturn, its rings and moons. After 20 years in space, NASA's Cassini spacecraft is running out of fuel. And so, to protect moons of Saturn that could have conditions suitable for life, a spectacular end has been planned for this long-lived traveler from Earth. 2004, following a 7-year journey through the solar system, Cassini arrived at Saturn.
The SOI burn attitude or pointing position, and light up the rockets.
The spacecraft carried a passenger, the European Huygens probe, the first human-made object to land on a world in the distant outer solar system. For over a decade, Cassini has shared the wonders of Saturn and its family of icy moons, taking us to astounding worlds where methane rivers run to a methane sea, where jets of ice and gas are blasting material into space from a liquid water ocean that might harbor the ingredients for life. And Saturn, a giant world ruled by raging storms and delicate harmonies of gravity. Now, Cassini has one last daring assignment. Cassini's grand finale is a brand new adventure. 22 dives through the space between Saturn and its rings. As it repeatedly braves this unexplored region, Cassini seeks new insights about the origins of the rings and the nature of the planet's interior, closer to Saturn than ever before. On the final orbit, Cassini will plunge into Saturn, fighting to keep its antenna pointed at Earth as it transmits its farewell. In the skies of Saturn, the journey ends as Cassini becomes part of the planet itself.
Wow. I don't know about anyone else. I feel quite emotional watching that. I can imagine that must have been extraordinary to stop that mission, to stop seeing that data coming through.
I'm sorry, I'm falling apart. My microphone has fallen off. Yeah, it was really interesting, you know. We almost wanted it to end because we were so tired. But then when it ended, I'm thinking, oh my gosh, what am I now going to do? So I found other things to do. But no, it was really emotional. Even watching it now, you know, I get a bit emotional. But I've become better at hiding it.
Brilliant. So we have now an opportunity for about 5-7 minutes or so to ask Michele questions about this extraordinary work that she's done. I'm struggling a little bit. I might have to stand up because I'm struggling a little bit. The light's shining right up at me to see if anybody's got a hand. Does anybody like to? Yes, the question here.
In the Titan magnetometer boom, you said you had two magnetometers, one from Imperial and one from JPL.
That's correct.
Why did you need like two? Why? And why were both from different agencies?
On an international mission like this, it's easier to get chosen if you've got international teams as part of your team. But we've always worked and collaborated with JPL. The reason we like to fly two is partly for redundancy, and on Cassini it's a really good thing we had to, because the one from the Jet Propulsion Lab stopped working just after we got there. But the other reason that we prefer to fly two is it allows us to calibrate the instrument. So what we need to know for a magnetometer is where the zero level of the instrument is. And that changes over time. It changes with temperature, it changes as the parts of the instrument age. And so if you've got two separated on a boom, you're able to work out, using data from both of those, what the zero level is. When the one from JPL stopped working, we then had to roll the entire spacecraft to allow us to do that. And that took a bit of persuasion. But it then allowed us to really calibrate the instrument.
I have one more just follow-up question. Did you also have a Langmuir probe for that to measure the plasma?
Yes, there was a Langmuir probe on board Cassini as well. Yeah.
The same boom, or it was a different boom?
No, it was on a different boom. Yeah, yeah.
Brilliant. Any other questions? So the man in the centre there with the grey hair. George.
I do feel like
That's
I'm
the
on
one,
20
yeah.
questions here. I can't see a thing. But anyway.
Thank you. Thanks very much. I'm fascinated by the idea of the water worlds and the fact that so many of them seem to have water ice. Could you expand a bit about what properties maintain that the state of the ice, whether pressure, temperature, and if so, what causes the temperature to be high enough for the water to be liquid?
So we think, and it depends on which theorist you talk to, but we think that for Enceladus, its orbit is not quite circular around Saturn. And so that means on some part of the orbit, it's closer to Saturn and its gravitational field than on others. And so tidal forces are keeping the interior of Enceladus warm. And we think similar things for the other three moons of Jupiter as well. So it's tidal forces on the interior which are keeping it warm. But no, it was a real surprise at Enceladus because it's really small. The fact that it still has an internal heat source after being formed so many millions of years ago was a real surprise. That's part of what's trying to be modeled at the moment, is how you can, well, you know, one of the weird things about Ganymede and Callisto is that you've got ice and then you've got water and then you've got ice. What are the pressures doing that allow you to maintain that kind of internal structure? And that's something we don't quite understand.
Brilliant. Next question, the lady right at the back.
And then there's a gentleman in the middle.
I know.
Here. Sorry, I shouldn't be telling you how to do your job. Sorry.
Next one, definitely next one.
I want to ask, when you use the magnetometer of the boom to measure the changing magnetic fields of the Jupiter moons, how certain are you that the changing magnetic fields are due to the water in the planet? But like, is there any other possible sources of changing magnetic fields other than water?
That's a really good question, actually. So that's one of the first things we want to do when we fly past Ganymede, for example, is we want to confirm that it is a liquid ocean. As far as being water, it's part of the modelling work that we do. But the reason I say we want to confirm is that the Galileo observations had two different ways in which they could describe what they saw. One of them was a strange internal dynamo field at Ganymede, and the other was having a liquid water ocean. They thought the data pointed more to the liquid water ocean than to the internal dynamo, but that's one of the things that we want to be able to confirm.
And the question here, thank you for being so patient.
Hello, Michele. I was just wondering about the complex molecules detected. Would that be as complex as amino acids, that sort of thing? Or?
No, it was carbon and nitrogen. I think there was some potassium as well.
Oh, right.
Yeah.
Because am I right? I read somewhere that amino acids have been detected sort of in the Orion Nebula region. Is that correct or not?
I don't know, actually.
Oh, right.
I don't know, sorry.
Thanks very much.
Yes, the lady with the red scarf, and then maybe, George, we could look online, see if anyone's got a question there.
And I thought I saw a hand at the top as well.
Oh, thank you.
I was just curious about what you hinted at, so why you were not concerned about...
Oh, thank you. Thank you. You took my hint. Thank you. So if you're going to land on a body where life might be found in the future, what we are always told we need to do is we need to put the spacecraft or the probe through what is called a planetary protection exercise. And that sounds really formal, but what you do is you zap it with high-energy X-rays to kill any bugs that might be on it before you actually launch it. And so if you had a really close look at the Cassini spacecraft, you would see the Huygens probe was standing away from the spacecraft on little arms, so it didn't actually touch the spacecraft. So that's why if we had found life on Titan with Huygens, we would have been able to say that we hadn't taken it with us. But it's really expensive to do that, so you don't do that unless you really have to.
Okay, I think there's another question towards the back. Jenny, is that right? Yes.
Just curious, are you able to say how advanced you think life could get in that sort of environment?
Based on what we know, I'm thinking bacteria at this stage. Really don't know any more than that. You know, one of the things about the Jupiter system in particular is the radiation environment is really intense. So that's why for Ganymede, it's protected by a magnetic field, so there might be the possibility of something being able to evolve underneath the protection of the magnetic field. But at this stage, I'm not going any further than bacteria.
Thank you.
So this gentleman here with the white beard, and I think that's going to have to be our last question, unfortunately, but...
Sorry, I went over time.
No, it was wonderful.
So there are two questions, because the last thing was... you said there was lots of radiation.
Yes.
Radiation from Saturn, or Jupiter.
Jupiter.
Yeah. No, I was thinking Enceladus, and that is Saturn, isn't it?
Yes.
All right. I thought, so which magnetic field is protecting the satellite? Which satellite is being protected by a magnetic field?
Ganymede.
Ganymede.
Ganymede, yes.
Is that not quite small, though?
Ganymede is about the same size as Mercury.
All right.
Yeah, so it's a reasonable...
Has a sufficiently high magnetic field to take it? Like
It's the only moon in the solar system that has a magnetic field like we've got on the Earth. Yeah. Yeah. And we don't quite understand why. That's one of the reasons we want to go there.
Wonderful. Well, thank you so much for your questions. I know there are people who have more questions for Michele, but I think we do have to sort of wrap it up there. I just have a few words to say. So Peter mentioned right at the beginning that this year's Athena Lecture forms part of our International Women's Week celebration. And I do want to specifically thank some of the many people who've been in the background supporting these things. So Jenny Lambert and George Ellis from the Provost's office, and Sheena Cardosa in particular, have done an incredible job at setting up a range of activities across this week. But of course, there's a whole swathe of other things that have gone on in departments and faculties as well as through our student body. So a phrase that's commonly used to describe women and, Imperial and its women is world leading. Meaning, of course, that we carry out research that changes the world and how we interact with it. But here we've heard about research that is quite literally out of this world. Our women act as beacons, inspiring the next generation of brilliant scientists, and Michele is a prime example of that. It's been an honor and a privilege to hear about this fundamental research that is changing our understanding of the solar system and beyond. And I thank you, Michele, for making the time to come and talk to us about it today. And I just invite you all to give her one last round of applause. And now my last words are there's food and drink outside, so please join us there. Wonderful. Oh my.